Good morning, all of you. Today, I, Manshi Kumari from BSc Chemistry Honors Final Year, is here to make a video for visually impaired students on the topic Uses of Organic and Inorganic Reagents in Inorganic Analysis. Introduction. Reagents are those compounds which are used in inorganic analysis for the detection and determination of ions and molecules. A large number of organic as well as inorganic reagents have been used for this purpose. The inorganic precipitating reagents generally precipitate the inorganic species as sparingly soluble salts or hydrous oxides. The organic precipitating agents form sparingly soluble products either through coordinate linkage or through ionic linkage between the inorganic species and the organic precipitating agent. Advantages of using organic reagents. The advantages of using organic reagents are listed below. First, they are more specific than conventional reagents under certain conditions. Because of this property, they can frequently be used to detect a single type of ion in a complex mixture. Second, they can be more sensitive. Classical semi-micro methods of qualitative analysis will usually not detect much less than 100 gammas of a substance under specific test solutions. Organic reagents, on the other hand, are capable of detecting below 10 gamma and in certain cases as little as 10 raised to the power minus 3 gamma. Third, they can be adopted in quantitative analysis. The organic precipitates are generally insoluble in water at a given pH and can be separated, dried, and weighed. Those reactions giving colored soluble product frequently show a regular change in color intensity with concentration of the substance under test and so are adaptable to an accurate comparison with colors representing concentration. This is the basic idea in branch of calorimetry. Common properties of organic reagents. Some of the common properties of organic reagents due to which these are used in inorganic analysis are given below. First, formation of colored precipitate. A. Organic reagents form direct characteristics color with the ions to be detected. B. For locating endpoint, that is as indicators employed in volumetric titration. Second, formation of precipitates due to difference in solubility. This may be made on the basis of gravimetric method. Third, extraction in organic solvent at controlled pH. Fourth, masking reagents. This increases the selectivity of reagents. Fifth, difference in volatility. Sixth, oxidation or reduction to other valency state. 7. Wash liquids. The chemical nature of organic reagent is important in determining the use of above mentioned properties. Advantages of organic reagents over inorganic reagents. It is due to the following properties that they are better precipitating reagents than inorganic reagents. First, selectivity. In many cases, organic reagents are somewhat specific. For example, cobalt from nickel using alpha nitroso beta naphthalone or dimethylglyoxime, aluminium from iron using cubeferron, cadmium from copper using quinolinic acid, and thiourea can be precipitated. In some cases, adjustment of the pH will often cause precipitation of one constituent alone. By changing pH and solvent condition, one constituent after another can sometimes be quickly precipitated out. Second, ease of drying. Organic reagents produce compounds that have little affinity for water and are dried easily at temperature low enough to prevent decomposition. Third, co-precipitation. Lack of ionic character of organic precipitation products greatly reduces co-precipitation. In most cases, for example, the cross-precipitation of sodium and potassium with magnesium is much less when the latter is precipitated by 8-hydroxyquinoline than what it is precipitated by phosphate or oxalate. Some exceptions in metals do occur. It has been little studied, but in some cases, as it is as Bad as in inorganic precipitants. Reagents are usually insoluble in water, therefore, it is important not to add an excess of reagent. This is difficult because there is no way to tell when sufficient reagent without excess has been added. Any excess that is insoluble would add to the weight of precipitate. Disadvantages of organic reagents. There are unfortunately disadvantages to using organic reagents. First, volatility. This is the first practical disadvantage of organic reagents because chelated compounds are non-polar. The forces between individual molecules in the crystals are not very great. The sum of the metallic complexes which are precipitated in analytical chemistry are appreciably volatile above 130 to 150 degrees Celsius and most decompose about this temperature. Therefore, the drying of precipitate should be done below 130 degrees Celsius to avoid decomposition. Second, impurities in reagents. It is very difficult to prepare an organic reagent of the same degree of purity as, say, inorganic compounds. Impurities present in the organic reagents may enter into the precipitate during the precipitation and cause undesirable reactions. For example, a dimethyl glycoxime exists in three forms, that is alpha, beta, gamma. Of these, only the alpha form is specific for nickel. While preparing dimethyl glycoxime, gamma form is also formed along with the alpha form. If the precipitation is carried out with this impure dimethyl glycoxime, the nickel will be precipitated with some other metals because alpha form is specific for nickel, whereas gamma form can precipitate other metals also. B. Ketoenol isomerism in such compounds as dithiazone will cause errors in calorimetric work unless conditions are carefully selected. Third, low solubility of the reagents in water. This is the greatest disadvantage which organic precipitants have in comparison with inorganic precipitants. Fourth, high molecular weight. The very high molecular weights of the chelate complexes formed with metal ions reduce proportionately small errors in the precipitation and weighing. Colored compounds. Chelate compounds are often highly colored, and since they are usually soluble in organic solvents, they lend themselves to calorimetric or photometric methods of analysis. Sixth, solubility in organic solvents. Because of their covalent nature, most metal complexes with organic reagents are soluble in non-polar solvents, chloroform being usually the best. Such solvents are used to extract the complexes for colorimetric determination, or they may be used simply for separating one element from another. Thus, the complex of cufuron with tripositive iron is very soluble in ether and chloroform, which allow one to remove large amounts of iron from solutions containing aluminium. In these extractions, the pH must be carefully adjusted to give the desired separation. Important organic reagents. Some of the organic reagents which are generally used in the identification of ions are discussed below. First, oxine C9H7ON. The structure of this reagent is given in figure. It is almost a colorless solid soluble in organic solvents and mineral acids. It gives yellow color, which may be due to the formation of quinoid structure. It was introduced by Ham and Berg in 1927 as analytical reagent. A number of metals give coordination complexes with this reagent. Examples of such metals are magnesium, zinc, copper, cadmium, aluminium, iron, thorium, etc. The formation of the complex compound with the bivalent metal like Zn2 positive is shown below. The quantitative estimation of the complex is carried out by drying and weighing the hydrated or anhydrous complex, or complex is ignited to oxide and then weighed. In volumetric methods, a precipitate is dissolved by filtering with hydrochloric acid and then resulting solution is titrated against standard potassium bromide solution. In spectrophotometric method, the estimation of the metal ion is carried out by measuring the optical density of the complex. The reagent has been found to be suitable for magnesium, aluminium, etc. The reagent is a 2% solution of oxime in 2-normality acetic acid. Second, dimethyl glyoxime. This reagent was discovered by L. Skarnguff and was applied by O. Brunk for the determination of nickel in steel. The structure of this reagent is shown in figure. This reagent gives an insoluble red chelate with nickel 2 positive ion in ammoniacal medium. For details, see applications of the formation of chelated complexes discussed in chapter on basic concepts of coordination chemistry. Solution of palladium salts give characteristics yellow precipitate in dilute HCl or H2SO4, but nitrate ions interfere. Solution of bismuth salts also gives a yellow precipitate in presence of EDTA at pH 11 to 11.5. For the studies, 1% solution of dimethyl glyoxime in alcohol is employed. In spectrophotometric method, the insoluble precipitate is extracted into chloroform, which yields yellow coloration, and then the optical density is measured. Third, alpha nitroso beta naphthalone, also called 1-nitroso 2-naphthalone. The structure of this reagent is shown at A of figure. It is an orange-brown powder having melting point of 109 degrees Celsius, soluble in organic solvent but almost insoluble in water. The reagent is usually employed as a saturated solution in 50% acetic acid. This reagent is common for the precipitation of many metallic radicals, but it is used specially for the detection of ferric iron, copper, and cobalt with palladium and uranyl salts in slightly acid solution. It gives insoluble colored compounds under suitable conditions. Nickel and magnesium, however, are not precipitated by this reagent. Therefore, the reagent in acid solution is used for the separation of nickel from cobalt. The structure of the chelated complex formed by this reagent with cobalt 3 positive ion is shown at B of figure 18.3. The reagent has also been used for the spectrophotometric determination of cobalt and a few other metal ions. It is also used for spot test of cobalt. Fourth, cubeferron. Cubeferron exists largely not in nitroso-hydroxy form but in tautomeric amine oxide form. The reagent is usually employed as a 6% aqueous solution but is most useful in strongly acidic solution. In strongly acidic solution, it precipitates Fe third, Ce third, Nb, Ta, W6, Ga, and Sn second, Cu second, etc. Precipitates should be filtered immediately after their formation because cubeferron is not very stable in acid solutions. Furthermore, precipitation should be carried out in cold since the reagent is decomposed into nitrobenzene on heating. The precipitates can't be weighed after drying but must be ignited to the corresponding oxide and then weighed. The formation of chelated complex with Cu2 positive ion can be shown as follows. Fifth, aluminone. It is an ammonium salt of orange tricarboxylic acid. Its structure is shown in figure 18.5. It is a brownish red powder freely soluble in water. It forms brilliant colored lakes with certain metals, especially aluminium, with which it gives a bright red lake. Aluminum is a dye and it is very important reagent for spectrophotometric determination of aluminium. By adjusting pH of the test solution below 7.8, it is possible to estimate 0.005 mg of aluminium even in absence of calcium. The reagent is prepared by dissolving 0.1 gram of the substance in 100 ml of water. 6. Rubinic acid, also called dithioxamide. This reagent is the diamide of dithioxylic acid and is an equilibrium mixture with its tautomeric acid diamido form. The Sc form combines with nickel, cobalt and copper to give colored water-insoluble inner complex salts whose composition is shown in figure 18.6. The copper, cobalt and nickel compounds are quantitatively precipitated from strongly ammoniacal solution. In strong mineral acid solution, rubinic acid react only with certain elements of platinum salts. In addition to above, rubinic acid forms colored compounds with silver, mercury, bismuth and iron. Rubinic acid is not only important as spot test reagent but also as a gravimetric and spectrophotometric reagent. Rhodamine B. It is tetraethyl rhodamine and is represented by the structure as given in figure. Solution of antimony fifth. Salts in strong hydrochloric acid react with rhodamine B and the aqueous solution of the reagent changes from red to violet or blue and finally divided precipitate separates immediately or after standing. Trace amounts of antimony may be detected in the presence of large quantities of tin by means of this reagent. Small amounts of iron do not interfere. Mercury, called palladium are precipitated, while molybdates and tungstates in acid solution give color reaction with rhodamine B, similar to those given by antimony salt. The freshly prepared benzene solution of rhodamine B is preferred to the aqueous solution. 8. Benzidine. Its structure is given in the margin in figure 18.8. It is a basic reagent and is employed in slightly acidic solution as dihydrochloride for the precipitation of sulfates as C12H12N2H2 whole raised to the power 2 positive, SO4 raised to the power 2 negative. The resulting precipitates may be titrated against standard alkali. The important drawback of the method is the relatively high solubility of the precipitate in water and even more in dilute hydrochloric acid. It also precipitates anions like phosphates and tungstates and give crystalline precipitates with a number of metallic ions such as silver, copper, cadmium, gold, zinc, etc. with cobalt 3 and Ti3. Benzidine yields a blue coloration in alkaline medium, which is an important spot test for the metal ions. Recently, benzidine in dilute acetic acid has also been employed as a spot test reagent for the identification of some platinum metals like osmium, iridium and platinum. 9th, cupron or alpha benzoin. Its structure is given in figure 18.9. It is a white crystalline solid. It is sparingly soluble in water but fairly soluble in alcohol. It also exists in isomeric beta form. Cupron is used as a reagent for the quantitative determination of copper, molybdenum and tungsten. Alcoholic solution of cupron gives a green precipitate with ammoniacal solution of copper salt. Precipitation of other metals in ammoniacal medium is prevented in presence of tartaric acid. The green precipitate is soluble in dilute mineral acids. Copper can be estimated both volumetrically and gravimetrically by this reagent. The green precipitate in an inner complex whose formation can be shown as. Cupron also precipitates molybdenum and vanadium ions quantitatively, but in strongly acid solution, vanadium gives a yellow precipitate, while molybdenum gives a white precipitate. Tungsten and palladium also appear to be quantitatively precipitated with alpha benzoin oxide. Fagel ATAL have recommended the use of reagent for the detection of basicity in slightly soluble materials such as Al2O3, BaCO3, etc. 10th, magnesium. The structure of this reagent is given in the figure. It is also called p-nitrobenzene azorresorcinol. 1 to 0.5% solution in 0.25 normality in NaOH is generally employed. In alkaline solution, it forms a bright blue lake with magnesium ions. The sensitivity of this test is influenced by the presence of ammonium salts, so their presence must be avoided. 11th, alizarin S. It is alizarin sulfonic acid whose structure has been shown in figure 18.1. It is a dye whose sodium salt is soluble in water and is employed as an analytical reagent. Aluminium salts give a red precipitate with the violet solution of alizarin S in ammonia. This complex is an adsorption complex of aluminium with alizarin sulfonic acid. Adsorption system of this type containing metal hydroxide and a dye stuff are called lakes. Zirconium fourth forms red violet colored compounds with the reagent under the alkaline conditions. Boric acid also forms brilliant red color in UV light by alizarin in H2SO4. The reagent has been employed as a spectrophotometric reagent for the above metal ions as well as for few others. Furthermore, its applicability as adsorption indicator in the titration of FeCN6 whole raised to the power 4 negative MOO4 whole raised to the power 2 negative has also been reported. 12th, nitron. Its structure is given in figure 18.12. It is a yellow solid. It is insoluble in water but dissolves in acetic acid. Its 10% solution in 5% acetic acid is generally used as a reagent. Nitron with nitrate yields a sparingly soluble crystalline nitrate C20H16N4.HNO3 in solution acidified with acetic or sulfuric acid. Thus, nitron is a gravimetric reagent for nitrate. Perchlorate, perrhenate, tetrafluoroborate, and tungstate also form insoluble salts and can be determined in a similar manner. Numerous other anions including bromide, iodide, chlorate, thiocyanate, nitrite, and chromate interfere but may easily be removed by preliminary treatment. The results in the presence of chloride ions are generally high, possible because of co-precipitation. 13. Salicyl aldoxamine. The structure of this reagent is given in figure 18.13. It is a white crystalline solid melting point 57 degrees Celsius, sparingly soluble in water. 5% solution of salicyl aldoxamine is 50% ethyl alcohol is used as a reagent. The reagent decomposes in solution and should not be kept for more than about 3 days. Salicyl aldoxime gives a yellow-greenish precipitate of the inner complex of copper. Salicyl aldoxime with acetic acid solution of Cu2 positive ions. Important inorganic reagents. Some important inorganic precipitated reagents are listed in this table as you can see. Precipitation of Al3 positive, Ca2 positive and Mg2 positive ions by liquid NH3 oxalic acid H2CO4 and NH4 twice HPO4 respectively can be shown as first, Al2SO4 3 plus 6 NH4OH changes to 2AlOH3 plus 3 NH4 twice SO4. 2AlOH3 ignite minus 3H2O Al2O3 plus 3H2O. Second, CaCl2 plus H2C2O4 at 135 degrees Celsius changes to CaC2O4.H2O plus 2HCl. CaC2O4.H2O at 2 to 5 degrees Celsius changes to CaC2O4, which at 450 degrees Celsius changes to CaCO3, which at 850 degrees Celsius changes to CaO. Third, MgSO4 plus NH4 twice HPO4 changes to MgNH4PO4.6H2O plus NH4HSO4. 2 MgNH4PO4.6H2O ignite changes to Mg2P2O7 plus 2NH3 plus 7H2O. Thank you.